Okay, so we are going to continue with some graphing things and just talking about maybe how linear and exponential growth or decay look in a graph. We'll also see things like compound and simple interest. I know we did see the compound interest formula earlier in the Passport to Advanced Math, and you're going to see that again in this section. So to start us off, we're just going to talk about linear relationships. So something is linear if it can be written in that form of y equals mx plus b. So it might not be in slope-intercept form, but essentially if we can write it that way, then we have a linear relationship. The one thing that you might want to consider here is that your highest power is x to the first power, or just x. So when you see those x squareds, x to the third, that's where you get into the quadratic and the cubic relationships. If you're looking at a chart to see whether or not something's a linear relationship, you want to make sure that it holds true for all of the values in the chart and not just the first few. So for example, maybe you see your x values and your y values. I don't know, you've got 2, 4, 6, 8, you're counting by twos over here, and then maybe over here you've got 0, 5, 10, 15. So for every 2 unit increase for x, you're increasing by 5 for y. So that's consistent. That gives you a linear relationship. But then maybe all of a sudden here, this last point, you only increase by 1, and then on y you increase by 5 still. Well, that's not still that same slope of increasing 2 for every x and 5 for every y, or 5 over 2. Now you're looking at 5 over 1. So this discrepancy here would make it not a linear relationship. On the next couple of slides, you're going to see some problems where we're looking at simple and compound interest. So I just want to make sure that we're clear on the difference. So something is, if you're told something is compounded with a simple interest formula, your formula is that amount, or how much money you have, is equal to the principal times rate times time. So think of it's pretty simple. Everything's kind of straight across on the same level. Whereas if you have compound interest, and the problem would say interest is compounded annually or semi-annually. So it would be clear, you're looking for this word compound, or you're looking for this word simple. Your formula for compound interest, the amount is going to be equal to the principal, so how much you invested, times 1 plus the rate divided by the number of times per year it's compounded, to the number of times per year to the number of years. So here's an example. I'll let you read this for just a second. Okay, so this tells us simple interest. That means we're going to be looking at that A equals P times R times T formula. So if we can remember simple interest, there's maybe no variables in the exponent, then we can just eliminate these two choices right off the bat. And then maybe we just need to figure out where to go from there. So then from there, plugging everything in, our amount is equal to the principal, so what we initially had, so $1,000, times the rate, which is 4%. So 4% is 0.04, but we need the initial investment and that 4%, so it's really 1.04 times the amount of time. And here they have time as K years, so we can change that to a K. So that matches choice A. Be careful, choice B here looks like it could potentially be in the running, but this is really 4% times the number of years, and then that 100% is added back in. So here we're taking 4% each year with the way that A is written. Okay, so then we have exponential growth. So something is considered exponential growth if the variable is in the exponent here. So this is where we see things like compound interest, because that time variable is in the exponent. So here's another example. It's very similar to the last one. And here the key is it's compounded semi-annually. So compounded means that we're going to use the compound interest formula. And then semi-annually, this means twice per year. which tells me that n is going to be equal to 2. So now I can start to piece things together. And even without knowing this formula here, if I can remember that compound interest is going to deal with variables in my exponent, I can get rid of those first two answer choices. So then from there, I've got it narrowed down to these two. And maybe without even plugging all the way into the original equation, I can remember that that exponent has something to do with how many times per year it's compounded. Well, here we've got the 2k. So that tells me that D is my correct choice. But I can build my formula just to see that it does match with D. So my initial principal is that $1,000. 1 plus my rate of 4%, so that's 0.04, divided by the number of times per year it's compounded, so twice, and then 2 times t, which in this case, like the last one, we're using k instead. So the only thing I need to do here is just simplify this fraction. So I've got 1,000 and then 1 plus 0.02 to the 2k, and then I can add this together to get the 1.02. Okay, so this next set of information on confidence intervals is probably something that's brand new information for a lot of you. This is something that you would learn about in statistics, but you don't have to know a whole lot about confidence intervals for the SATs to be successful. So a confidence interval basically gives you some estimate plus or minus a margin of error. So it would be like an average plus or minus some unknown, well, it would be known margin, or it might be a proportion or a percent plus or minus some margin. And so really what you need to know for the SATs is it gives you a range of what's reasonable for some parameter. So what's really happening here is that you, if you want to make some sort of a claim about a population, you typically can't measure every single person in the population. It's just too time consuming or it's too costly. So instead, we want to make a claim, we'll say about the population mean, or population proportion, and we do that from sample data. So we use this subgroup or a sample to come up with some estimate. So it's a sample mean, a sample average, or an estimate or a sample proportion to come up with what we think the population mean or the population proportion might be. But because there's what we call sampling variability, we don't expect the sample value to match the population exactly. We have this margin of error. So that margin of error basically gives us a window of what's reasonable for that actual mean or for that actual percentage. So all you really need to know is that it tells us what's reasonable. So here this says a study estimates with 95% confidence that the percent of individuals with smartphones is 97% within 1.5%. This within is telling you this is your margin of error. This is your estimate. This 95%, that's statistically meaningful, but as far as the SATs go, we don't have to worry about how confident things are. We just need to know that their estimate was 97%, their margin is 1.5%, so really that's 97 plus or minus 1.5. That gives us a window of what's reasonable for the actual population percent to be. So my lower bound, if I take 97% minus 1.5, that's 95.5%. If I then take 97 plus 1.5, that's 98.5%. So I'm basically saying, based on my sample study that came back at 97%, it's reasonable to believe that the population percentage is somewhere between 95% or 95.5% and 98.5%. So that's really all you'd have to identify with confidence intervals on the SATs. It's just what's reasonable or not reasonable. So maybe if it was a multiple choice question, they might give you this scenario and then say, what's reasonable? And then give you some choices. And maybe you'd have 94, 96, 97, and we'll say 98. Well, 98 is within range. Same with 97 and 96. 94 is not. So that would be the value that's not reasonable to believe that it's the population value. So here's an example. Okay, so here it's a 95% confidence interval. And again, that 95% is statistically meaningful, but we don't have to worry about it for the SATs. So we really can eliminate these two answer choices. What we're really interested in is this window of 324 to 360 camera pictures. So what this is telling us is that it's reasonable to believe that the average life of the batteries produced on that particular day is between 324 and 360 pictures. And we do want to kind of be careful. The last choice there is all batteries ever. Well, there might be something different about batteries produced on that particular day. So because they were only selected from that one day, we really can only make conclusions about that same particular day. Okay, so for your assignment, you've got linear and exponential growth and data inferences.